basically tells us about simple one concept of physics, and that is as long as you do not disturb an object for its own motion or during its own motion, the object will continue to maintain that state of motion. And what is that state of motion? That could be rest, like you are sitting somewhere right now, this is a state of motion. Or if you are moving or if you're walking down the street, that is also a state of motion. So both of these two conditions will be maintained by that object if no external force acts on it. So let's write down the definition. I would recommend noting down these definitions from the book. The most accurate form, you will find it over there. I'm just referring them, or I'm just discussing what that rule or definition means and how to understand it. So the first law basically tells you that an object continues to maintain its state of motion, and I'm adding this information from myself, that be that rest or motion, unless disturbed by an external force. So that would mean that if a truck or if a car is already moving, it would prefer to keep moving for the rest of its life if no external force acts on it. But why don't we see that happening in daily life? Because if, for example, the car is already moving in this direction, and if you switch off the engine, ideally speaking, it should maintain its state of motion. But why does it eventually slow down and stop? Okay, so can you hear me now? Can you hear me back? All right. I just had electrical issues at my end, so I'm just now using my own phone's internet connection. All right. So I was discussing previously that if the car is already moving towards the right side, ideally speaking, it should still be moving towards the right side. Why is it not doing so in the real life? Because there is an external force or external factor that is trying to stop it from moving. And what is that external factor? That is the friction or the drag, right? So from the real life situation, yes, yes. So if this object was in space where there is no atmosphere, when there is no air, then of course it will continue to move in the same direction as it was before. All right. So this is the Newton's first law, and another word that actually summarizes all of this, or you can say that actually tells us more about this idea, is inertia. Inertia is the quality of an, let me write down the definition as well. It is the reluctance of an object to resist a change in its own motion. Now, what do I mean by that? It's just the resistance of that object against that external force, that does it want to change its position or not. So, for example, if I asked you to move a truck from its own position, if the truck was stationary or even if the truck was moving, and I would ask you to stop it, both of these tasks are difficult for you to achieve. You cannot provide enough force to eventually move the truck, and of course you cannot provide enough force to eventually stop a truck if it's already moving. But if I had asked you to do the same thing for a tennis ball or a ping pong ball, then of course you would be able to do that task, right? So this inertia basically tells us whether this object is easy or difficult to move from its location, or whether it's easy or difficult to change its motion, whatever that may be, right? So these qualities are referred as inertia. So it's basically the resistance of that object. It's just trying to tell you that no, I don't want to leave my position. Or if it's a lighter object, it still does the same thing But since you have more strength in that object, you will eventually cause it to move. So, but what quantity does it depend on? So inertia depends on the mass of that object. So more massive an object is going to be, naturally more inertia it will have, and naturally or obviously it's going to provide or it's going to exert a greater force against any external force that is asking that object to change its motion or type of motion. Do we understand up to this point? Yes? So if I had to talk about inertia, the inertia of a simple truck or a simple vehicle that's trying to move will be much greater than a tennis ball. So inertia of my truck is much greater than inertia of a simple ball. So let's go back to the definition of the first law. This is what inertia is, and let's read the definition of first law again. Try to read the definition again and try to find if it's different from inertia or if it's saying the same thing in a different way. Yeah, 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 but they're saying the same thing. So we can conclude the first law in terms of inertia, right? So they are just same things with different names. All right. So this is my first law, and this is about balanced forces. Now, when I say balanced forces, that means that it doesn't matter how many forces are acting on the object, everything is balanced. For example, if there was another force, forward force by the engine pulling the truck forwards, there was a drag force in the backside, let's say there is a weight component, and then we have a normal reaction opposite to this one. So if I say that this is following the first law, that would mean that the forward driving force and the backward drag or friction, they are all equal. So the driving force is equal to the friction, right? And the weight is equal to the normal reaction. They are both equal. And under these circumstances, if I wanted to change its motion, then I would have to add another extra force. If I want it to accelerate or to speed up, I'll have to help the driving force by adding an unbalancing effect. If I want it to stop, then I would have to help the frictional forces to eventually cause it to stop. But as long as the forward and backward forces are equal in magnitude, the object will continue to maintain its state of motion. Now, notice that if it was already moving in this direction and the forward engine force and the backward friction force were equal, then the object would maintain its constant speed, which over here I've referred as motion. It will keep on moving at the same speed. But if the truck was stationary on a road, for example, it's not moving right now, and the engine tries to provide a force forwards, so the truck will not start moving until the forward driving force does not overcome or dominate the frictional force. Do you understand this point? Yes? All right. So this is what the first law is about. It's about balanced forces, and if somebody tries to unbalance or tries to create an unbalance, then of course that will become something else. But right now it's about balanced forces. So now we move towards unbalanced forces, broadly speaking about Newton's second law. So the second law says that if a force is applied on an object, then that mass will experience an acceleration in the same direction This is very important to understand, in the same direction of the applied force. And one more thing that there is, that force and acceleration are directly proportional. This is another point. So we develop the idea from this point onwards that if they are both directly proportional, let's try to think what that means, right? So what we're saying right now is that force is proportional to acceleration. This is what the same thing that I discussed over here, that if you want this object to accelerate, then you'll have to create some unbalancing effect, or you will have to create an effect in which the driving force dominates or is greater than the friction or drag. If you want this to slow down or to break eventually, right, then the drag forces and friction forces would have to be greater or would have to be more dominant than the driving force. So whatever force or whatever direction you want to favor, in that direction there should be a force. So force proportional to acceleration, right? So greater the force, greater will be the amount of acceleration, and you experience this in every day as well. If you try to push a chair with a normal force, it travels some distance. If you try, or if you apply a very great force or a large force on that object, it may eventually fall further away from the previous case, right? Similarly, if you throw a ball upwards with a smaller force, it goes to a smaller height. If you throw with a larger force, it will eventually go to a larger height. So this is what Newton's second law tells us, that force and acceleration are proportional and they are in the same direction. What does that mean? Why we are emphasizing that? For example, I'm telling you that the object is already moving in this direction, right? If I wanted to accelerate, I will apply an unbalancing force. Remind you that this is an unbalancing force. I'm not saying that there are no forces acting on the object. There may be some forces acting on the object, like in this case, but I'm adding the unbalancing effect, right? So let's say that there's an extra force in the forward direction, then the acceleration will also be produced in the same direction. Now this gets particularly confusing if I talk about in this way, that if the object was already moving in this direction, it's already moving in this direction, right? But now I apply a force in the backwards direction. So now it accelerates in the backwards direction. But mind you, of course, since it's already moving in this direction, I will call this case as deceleration. Do we understand the point that the both factors are in the same direction? What do we mean by that? Right? The acceleration will follow, yeah. Yes. Okay, so let's try to give this a formula. And this is one of the most important formulas in physics. It's going to be used many, many times over, again and again. So we have F equals to M, sorry, not this way, but force proportional to acceleration. Let's convert this proportionality into inequality. We have force as it is, and we have acceleration as it is. Now we need a constant of proportionality that is simply coming, or you can say this is simply due to the mathematical reasons. There is no specific reason in terms of physics that we're introducing a constant. It's simple mathematics that if y is proportional to x, then if I want to write down y equals to x, then I'll have to introduce a constant and then write x. That actually governs this equation mathematically. So over here in this case, in Newton's law, mass is considered to be constant, or is supposed to be constant. So this is not my force, it is basically the net force. What do we mean by that? We'll get to that later. So this is mass represented in kg, this is net force represented in newtons, and this is acceleration, again in standard units, that would be meters per second square, right? So what do we mean by net force? That would mean we are not talking about a single force, we are actually talking about a multiple of forces which may have been combined to form a single force. Let's say I tell you that the forward force in this case is 50 newtons, this one is, let's say, 100 newtons, this one is 30 newtons, and this one is again 20 newtons, right? So if I ask you to find the net force, and if I ask you to find the acceleration, if the mass of the object is given to you as 2 kg, and I want you to find out the acceleration, then we will surely apply the formula F equals to ma, but over here in F, we cannot put a single force. 20, 30, 50 or 100, they will not be put in this formula as a single entity, rather a combination of all the forces. You see, when we say net forces, that means, or net force, that means what is the combined effect? I will write this word over here again, combined effect. That what's happening, or what is going to be the effect of all the forces if they acted at the same time on this object, right? So we have two forward forces, so I can combine them together because they are helping each other and they are in the same direction. Now I also add a positive sign because I want to find the addition of all the forces, because I said the combined effect of all the forces. Now when I write down the second part of the forces, I realize that they are opposite to 50 and 100, right? So, and of course they're in the opposite direction, so in vectors we represent the opposite vectors with a negative sign. And we have also discussed this point previously, that in physics we consider the right side and upper side to be positive, and the left side and downward sides to be negative. It's your choice. You can also consider the opposite or the other way around, but this is what we generally follow. So the left side forces are negative, so we write down minus 20 and minus 30 equals to, the mass is given to us as 2, acceleration is what we need to find out, so we are left with 150 minus 50 equals to 2a. This becomes 100 equals to 2a, and acceleration comes out as 50 meters per second square. So this acceleration, in which direction would it be? It would be in the direction of the dominating force, because if I narrow it down, this is what it looks like. 150 opposed by a force of 50 newtons. So of course, the dominating direction will have this acceleration of 50 meters per second square, right? This is the full understanding of Newton's second law. And one more thing, of course, what students generally do is try to make things simple for them instead of getting into this positive and negative situation. What they do is they combine the question like this, that all the forward forces minus all the backward forces. So this question simply becomes 150 opposed by 50 newtons and the mass is 2 kgs. So this is 150 minus 50 equals to 2 into A. Now mind you, I'm telling this you again and again, that F is not a single force. It's a combination of all the forces. So what we are left with over here as 100 newtons may seem to be as a value of F, but it actually came from two forces, 150 and 50. Any issues up to this point? Yes or no? All right. So this is our Newton's second law. It talks about the unbalancing forces or unbalanced forces. Let me create another scenario for you. This is unbalanced forces causing acceleration. Now, to combine the first and second law over here, if I had drawn the situation like this again, like this, that the forward force, for example, is 500 newtons, the backward drag is 500 newtons, the weight of the truck is 700 newtons, and the normal reaction provided by the ground is 700 newtons. Let's say that the truck is already moving but has these circumstances. So it will be moving at a constant speed because forward and backward forces are equal. If I apply the Newton's second law under these circumstances, what I'm going to get is F equals to ma, the pulling force, which is 500 forward force, minus the stopping force, which is at the back. I get mass into acceleration, and I'm certainly going to get acceleration as 0. That is why I'm saying that it is going to move at a constant speed, because there is no unbalancing effect. Now let's try to introduce an unbalancing effect in this situation. Let's say that we introduce an extra force of 100 newtons in the case. So Newton's second law actually deals with this unbalancing force. It does not care about the fact that how many other forces are acting on the system. It doesn't. All it cares about is what unbalancing effect has been produced. That is why the second law is about, or is revolves around, the unbalanced forces. That's all it talks about. So even in this situation, if I narrow it down, this becomes 100 newtons forward. So this is that unbalancing force that has created an unbalancing effect in the system, which eventually led to an acceleration of 50 meters per second squared. Right? So do we understand what is the meaning of balancing or balanced forces and unbalanced forces? Yes? All right, all right. So the third topic, and of course, we will get to this formula F equals to ma in great detail in the chapter of momentum once more. So over here we have Newton's third law. Arguably the easiest one to understand, but the easiest one again to actually misunderstand it as well. So this is Newton's third law. And again it says that action and reaction are opposite and equal. But one thing that we generally miss about this definition that is required at least at O levels and A levels is that it acts on mutual exclusive bodies. What do we mean by mutually exclusive bodies? Let's take an example. Let's say that we have a table. This is my table, and this is the stand where the table is actually standing on, right? And I have a book on top of the table. So I'm going to draw a few vectors. This is the weight of the book, and this is the normal reaction provided by the ground to the book. So it's as simple as this. If you're sitting down on your chair or your bed or your sofa, your weight is pushing down on that sofa or chair. That sofa or chair is applying a counteractive force on you as a normal reaction. And we know that the normal reaction is coming from the molecular forces. If I analyze this a little deeper, the molecules of the table are trying to stretch a little bit under the weight of the book, but due to the bonds between them, they are providing a counteracting force to this book and preventing it from falling through the table. This is the discussion that we had yesterday, yes? All right. So my question to you with values that if the weight of the book is 15 newtons, the normal reaction will be 15 newtons because they're not moving. That means they're stationary. That would mean that both are equal. Nobody is greater than anyone. So they're basically equal. Now they're equal and opposite. Do they make the Newton's third law action-reaction pair? The word I'm using is pair. Can I call normal reaction and weight as pair or following the Newton's third law? Alright, no, this is wrong. We cannot call them Newton's third law because we are fooled by the first part, that is action and reaction are equal and opposite. This is what we generally think about Newton's third law, but it's not that simple. The second point, that is the mutually exclusive bodies, is what we need to understand right now. The thing that it's trying to tell you is that the cause of those forces should be the same. If they both have, if they don't have the same cause, then they will not be acting or they will not be a part of third law. What do we mean by that? Now let's say if I include, is the weight of the book due to the table? Is the table making that weight? No. The weight is basically due to the planet or due to the earth, right? So the cause of the weight is the earth, but the cause of the normal reaction is the table. The cause is different for both of these cases. So although on face value they look the same and equal and opposite, but they're not. Their cause should be the same, which in more complexity is said like this, is usually discussed like this, mutually exclusive bodies. So that's all it's trying to say. Their cause should be the same. Now let's try to figure out, is there any third law pair over here or not? Yes, there is, but we'll have to identify that on our own. So are we familiar with Newton's law of gravity? Yes, are we familiar by that? Are we familiar of the Newton's law of gravity? Okay. So masses, it simply says masses attract each other. That is all. So if I consider myself as a mass and the earth as a mass, then I am being attracted by the earth, which makes the weight of the object. But I'm also attracting the earth towards myself. We are both attracting each other by the same amount of force. So this is the Newton's third law, right? And one more question that I would have in this scenario is that if I jump off a building, I would be seen moving towards the earth. But will anyone ever see the earth moving towards me, although the force is same on both objects? Would I ever see that? What is the reason for that? Why don't I see the earth moving although I'm applying the same force on it? So why don't we see that happening over here is because of the inertia of the earth. Inertia says that an object does not want to move from its location if a force is applied on it. So the earth is more massive, the earth is more massive, we are less massive, so we end up moving towards the earth rather than the earth moving towards us. Okay, so over here, if I had to identify the Newton's third law pair with the weight of the book, then that would be this factor. That will also be 15 newtons. Now let's identify which factor is because of what factor. So this component, the red component that I'm seeing right now, is because of the earth, right? And the blue component that I'm seeing right now is because of the book. Now let's try to apply the definition on both of these forces once more. Let's try to identify the cause. The cause of the weight of the book was gravity, right? And the cause of this force by the book on the earth, pulling it towards itself, is also gravity, right? So these both objects are attracting each other towards each other, and the cause is the same. So in order for any two forces to be identified as Newton's third law, their cause, their producer, their maker should be one, or should be because of one cause. It could be acting on different objects, doesn't matter, but their producer should be the same. So the normal reaction is coming from the table, it's not coming from the earth. That is why, although it looks as if, but it's not the case. So the normal reaction and weight is the very first misconception of the Newton's third law, that on the face value it looks like that, but it's not. So that is why yesterday or in the previous lesson I went into great depth to make you understand that the normal reaction's cause is basically the intermolecular bonds of the table's surface molecules or atoms. It's not the earth. So that understanding or that discussion has helped us now to identify that this is because of the table, not because of the earth. So it cannot be qualified, or it cannot be qualified or taken as Newton's third law pair. Do we understand this misconception? Yes? And please note this idea, this will be frequently tested in A levels, and this is the very first misconception that the examiner in A levels and O levels will test from you. Alright, so let's move on to another example. For example, an object is freely falling under the influence of gravity. It has a parachute and it opens up that parachute and experiences, let's say, some form of drag, and there is a weight. Now let's say that the weight of the object is 50 newtons and drag combined on the whole parachute is 50 newtons. If I make this into a simpler object, this is what I'm looking at. 50 newtons of weight and 50 newtons of drag, right? Is this Newton's third law? Yes. The drag is there because of the air molecule or the inertia of air molecules inertia. Why do we feel air rushing across our body when we try to run through it? Because the air molecules that are already present there, which you are trying to move through, are trying to resist so that you don't displace them from their positions, right? So basically, the drag or the air resistance is just the inertia of the air molecules trying to stop you from moving through them. Similarly, the reason for that drag is air molecules, and the reason for weight is Earth's gravity. So if I had to identify again for some reason that if whether this is Newton's third law or not, then I would have to identify the Earth like this and Newton's third law or the gravitational attraction by this box on the Earth should have been identified or should be identified. So this is also the weight as 15 newtons. So let's summarize this, or to avoid any confusion, weight of any object in the universe will never make a third law pair with any other entity except the planet that we are talking about. So unless there is a planet involved, the weight of any object will never or not be considered for the Newton's third law pair. Do we understand this trick point? Yes. So this idea helps us to narrow the examples or at least eliminate the options that we have in MCQs. That if he gives you an option, let's say that let's try a question over here. Okay, so this is my Earth, the this is the sun, this is the Earth, and this is the moon. Let's say. So of course the sun is being attracted by the Earth and the Earth is being attracted by the sun. Similarly, the Earth is being attracted by the moon and the moon is being attracted by the sun. Also, the sun is being attracted by the moon and the moon is also being attracted by the sun. So all these situations are also Newton's third law pair. Everything else with weight and gravity will never be Newton's third law. One more example. Do you remember that we discussed tension yesterday between the rope and an object? And we remember that we concluded that tension will always be in two directions. If there is an upward tension, then there will also be a downward tension. This is also an example of Newton's third law, action-reaction pair. Because the rope is not generating any force, it's just transmitting. It's just a mode of transmission by connecting two objects and inflicting or representing the force of resistance of both objects onto each other via its own molecules. It's not providing any force on its own, it's just transmitting the force or the strength given by the other object. Do we understand this point? Yes? So this is also Newton's third law, right? Okay, one more thing and a few more things. For example, if we have a nucleus and if we have the valence electron, I'm sure that you're familiar with the nucleus and electron model. Yes, very common for a science student. Okay, so these are the electrons and this is the positively charged centrally placed nucleus, and this is my electron, and there is another force between them. So we know that positive and negative charges attract each other. Yes. So this negative charge is being attracted by the positively charged nucleus. Similarly, on the same time, this positively charged nucleus is being attracted by the valence electron as well. So this electrostatic force will also make the Newton's third law pair. You see, the reason for both forces is the same. So this force is being generated by the positively charged nucleus and this force is being generated by the electron. So the bodies are mutually exclusive, but the reason or the origin or the maker or the cause is same. Both forces have the same nature. They're both electrostatic force. Similarly, between the two magnets, between North and South Pole, they both attract each other. This is also Newton's third law. Because the nature of the force acting on both objects is magnetic, the bodies are mutually exclusive, and the action and reaction is equal and opposite. So do we understand how we visualize Newton's third law? So similarly, if you are in a swimming pool, let's say, and you are standing, let's say you're about to kick off or push the wall so that you move in this direction. Yes? This is also Newton's third law. Similarly, if you're standing, let's say, and this is the ground and this is the football, if you try to kick the football, the feeling that you feel in your feet that you have kicked something is because of the Newton's third law, because you applied a force on the ball and the ball applied a force on your feet, which is why you feel when you're holding something, even when you're holding a pen, why do you feel that there is a pen in your hand? Because your fingertips are applying a force on the ball or the ballpoint, and the ballpoint is applying a counteractive normal reaction force on your fingertips. Do we understand the universal level of Newton's third law? Okay, so that is all for today. Tomorrow we are going to start the next topic, that is stability and momentum, right? I will be sending the slides of this lesson after the class ends. That is all for today.